In this talk, because of the topic of the conference is computational intelligence, with which algorithms have contributed to improvements in agriculture use. Okay, so I'm going to present you here a random forest algorithm, and I'm going to tell you how you can use the random forests, okay, for SNP selection in rice. Because I think it's very much easier to introduce an algorithm with an illustrative example. I will not use a biological example for introduce you the algorithm. Okay, I'm going to work with a very toy problem. Okay, a movie data set, but you can extrapolate this kind of data for all data you would like to extrapolate it. Okay, so we are going to work with biological data, but here to introduce the algorithm, I think it's much better to use this toy problem. Okay, so we have a data set here where each sample is a movie, okay, and each feature is a country, star, or gender, and we want to predict if the movie is going to make success or not. Okay, if we think about a biological data, okay, each feature here can be, for example, I don't know, a SNP, okay? And the target attribute can be, for example, the productivity of rice, okay? So, a random forest is made of decision trees, okay? So what's a decision tree, okay? This is a decision tree. So in decision trees, internal nodes represent features, okay? Edges represent feature values, and leaf nodes represent target features. Okay, so we want to build an algorithm to construct this kind of tree, so we can make decisions on our data. So when we talking about selecting SNPs, okay, so each internal node here will be a SNP, okay, an SNP, and then the tree will contain the most important SNPs for a given problem. For example, predict the productivity of the rice. Okay, so a decision tree is used to classify instances. So the objective is to classify the larger number of instances with the smallest possible tree. If we have the smallest possible tree, it is supposed that this tree will contain the most important features of my data set. In our case, the most important SNPs, okay? So it's the induction algorithm to build a decision tree is a recursive algorithm. So the induction algorithm recursively partition the training set until the subsets obtained with the partitioning contain data from a single class or data from a pure type of prediction. So for example, if you want to predict the productivity of the rice, we want to produce subsets of samples of rice that have the same productivity, okay? Okay, so going back to our toy example here to see how a decision tree works. Okay. So if we select the feature country to start constructing our decision tree, okay? What we do, we create a node country with the feature country, and then we create edges for each values of that feature. So if we go back here to our toy data set, we see that for the feature country, we have 3 possible values for this feature country, okay? USA, Europe, and other. So if we choose the feature country, how is it going to divide our data? So we are going to check this. Okay? Looking at the classes or looking at the value of the target attribute we want to predict. Okay, so country, if country is equal to USA, we have 3 movies that are going to make success and 1 that's not going to make success. The same for Europe, the same for other. So if we look here at these subsets, we can start making some conclusions, okay? So if we look at the star feature, okay, if we use the star feature to divide our data set, okay, how does the star feature divides our data, okay? So if star is equal to yes, we have this kind of division. if star is equal to null, we have this kind of division. Okay. What if we took the feature gain here? Okay. So if we get the feature gain here, it has 3 possible values, and it divides our data set according to these 3 subsets. Always remembering here that we have movies that are going to make success and movies that are not going to make success, okay, depending on the value of the feature gainer. So what feature to choose? We have to look at the subsets that are created with the division of the feature. Okay, so if we look at, for example, here in the subsets created by the feature country, let's try to see how are the subsets that were created. Okay, if we look at this subset here, okay, so for the value, sorry, if we look at this subset here, for the value other for the feature country, we have only data for the class no. So this is a very good division. Okay, if we get the value USA, okay, the value USA results in a data set with 3 samples from class yes and 1 sample from class no. So we have much more samples from class yes than from class no. Okay, it's a good division. However, if we, for the value Europe, the subset of instance generated is not that good, okay? Because we have 2 samples for each class, so we cannot conclude anything. So the objective of building a decision tree is choosing features to be put in the tree so that these features generate subsamples that are pure, okay? In this case here, subsamples where movies belong to only 1 class. In case of productivity of rice, subsamples where the samples there in that subset belong to have the same productivity, okay? Belonging to the same class of productivity, for example. They are all very productive. So looking at the tree, we are going to know what features, in the case of the rice, what SNPs are going to be good for a high productivity of the rice, okay? So we are going to make this analysis for all features of our data set. Okay, but how to choose, okay, a good feature to be put in a data set, to be put in a decision tree? Okay, we have to use statistics. So statistics has measures that allows us to evaluate these previous situations here, to see which feature is the best one to be put in the decision tree. Okay, so we are going to use entropy, okay, which is a measure that measures the uncertainty of a random variable, okay, and quantifies to what extent the data are spread out over its possible values, okay? And we are going to use information gain. The information gain calculates the reduction in entropy. So we are going to select the feature that offers the higher information gain, okay? So we are going to calculate the entropy for a data set, and then we are going to calculate the information gain for each feature and select the one that reduces the entropy the most. Okay, so the entropy, the higher the entropy, okay, the more confusion I have in my data. So we want to select a feature that decreases entropy. So the feature that decreases the entropy gives me the highest information gain. So that's going to be a good feature. Okay, how do we calculate entropy, okay, for a data set? So if we have a data set with 2 classes, positive and negative, okay, we calculate the entropy by this formula, where P1 is the probability of observing the positive class, and P0 is the probability of observing the negative class. Okay, so entropy value is closer to 0, low entropy, means that the data is concentrated near 1 value. So think about the productivity of rice. We want to find the best decision tree, okay, to predict productivity of rice. So a good decision tree will have subsets of samples in my data set where I mean subsets of samples in the decision in the leaf nodes of the tree. So these subsets of samples, okay, in the leaf nodes of the decision tree will be concentrated nearly one value of productivity, okay? High productivity, low productivity. So then we can distinguish between different samples with different productivities. Entropy is close to 1. High entropy means that the data is spread out as much as possible. So there is confusion in data. I cannot make any decision. So we want to find a feature that decreases entropy. Okay, so the entropy for an entire data set, okay, is calculated this way. So getting our toy data set, remember we had 5 movies, 5 from the positive class and other 5 from the negative class. So we calculate the probability of the positive class, the probability of the negative class. Okay, when we put this in the formula, we have entropy equals to 1, which is the highest possible entry for this data set. Okay, there's total confusion in the data set. 5 instances from one class, 5 instances from the other class. So now we want to find the features that decrease this confusion. Okay, so the information gain of a feature now is going to reduce the entropy, okay, when I select a given feature. So I want to choose the feature with the highest information gain. So in our example, the information gain for each feature is going to be given by these formulas here. So the information gain for country is going to be the entropy for the entire data set minus what I'm calling here the remaining entropy for the country feature. The remaining entropy for a given feature is the expected remaining entropy after testing that feature. So we're going to select the feature that gives the higher information gain. So think about that. When I get my original data set, the entropy is very high. Okay, so now suppose I choose a given feature A. Okay, and now I'm going to calculate entropy for that feature A. Now suppose the entropy of the data set after selecting the feature A is very low. Okay, so I'm going to subtract the original entropy from this remaining entropy, the entropy of the feature A. So I'm going to subtract a very small value from a big value. So the result is going to be information gain very high information gain. That's going to be the best feature to be chosen. Good. So if we have a feature A now with D distinctive values, okay, this feature is going to divide our training data into E subsets. Okay, each subset has, of course, positive and negative instances. So the remaining entropy for a given subset, okay, is going to be given by this formula, where we are going to get the positive instances in a subset divided by the positive and negative instances in the subset, okay, for the calculation of positive and negative, okay? So this is going to be the remaining for a given subset, and we are going to have to calculate this for all k subsets. So to calculate the expected remaining entropy for all values for a given feature, okay? So I'm just checking if feature A is a good feature to separate my data. We have here to calculate the expected remaining entropy when we select feature A. So this is expected remaining entropy is calculated by this formulation, okay? Where we are going to calculate here the entropies for all subsets of features, all subsets of samples generated when I choose, okay, generated by one division that's performed with feature A, okay? And then the information gain after selecting feature A is going to be the information gain for the whole data sets minus the information gain for the feature. And we are going to do an example with this. Okay, let's perform a calculation with an example. So let's get the entropy for the feature country, okay, and let's calculate it. And then we're going to perform the same thing for the other features to see which feature is the best one to construct our decision tree. So if I get the feature country and see how this feature divides my data, what I have to do now is to calculate the remaining entropy here, okay, the entropy for each subset. So the entropy for the subset that resulted from using the feature country to divide the data, and the subset resulted from the feature country being equal to USA, the calculation is going to be like this. Okay, so the entropy for the feature country being equal USA is 3 divided by 4, log 2, 3 divided by 4, okay? And 1 divided by 4, log 2, 1 divided by 4, okay? So minus this, okay? The resulting calculation is going to be this value, okay? And we are going to perform this calculation for all the subsets. So this subset now, so I'm doing the calculation for the positive and negative instances, putting in the formula here and getting the entropy. So look, the entropy for this subset is the highest possible entropy for it. So it's 1, okay? So when I look at this subset, I can make no conclusions about the data. When I look at this subset, I can make some conclusions. Okay, most of the data belong to the positive class. So probably if an instance is similar to the instances here in this subset, so it's going to belong to the positive class. Okay, now I calculated the entropy here. The entropy here is the smallest possible entropy, okay, because this subset is pure. Okay, okay, good. Now, how do I calculate the remaining entropy for the feature country? I have just to sum up all the entropies calculated for each subset constructed using the feature entropy, okay? So we have to do 4 divided by 10 feature, 4 divided by 10 multiplied by the entropy USA. Why 4 divided by 10? Because if we look at here, we have 4 examples, 3 plus 1 divided by 10, because all the data set has 10 samples, okay? So it's 4 divided by 10, the entropy in this subset, plus 4 divided by 10, 4 divided by 10, so multiplied by this entropy, plus 2 divided by 10 multiplied by the entropy calculated for this subset. So the remaining entropy for the feature country is 0.7244. So we are going to perform these calculations for all the other features. Okay, so we got the feature country, we checked the subsets created when using the feature country to divide the data, we calculated the entropy in each of these subsets, we sum up these entropies, and the result is the remaining entropy for the feature country. So we're going to do the same for the other features, okay? Good. But first, having the remaining entropy, of course, okay, for the feature country, we are going to calculate the information gain for the feature country. So the information gain for the feature country is 1, which is the information gain for the whole data set, minus the remaining entropy for the feature country, which gives us the value 0.756. Okay, so keep this value in mind because this is the information gain of feature count of the feature country. Now we are going to perform these same calculations for the other features. Okay, so getting the feature star, remember feature star has 2 values. So the entropy when choosing value yes is 0.9852, and the entropy when choosing feature star for the value no is 1. So the remaining entropy, okay, is 7 divided by 10 entropy yes plus 3 divided by 10 entropy no. Why 7 by 10? Because I have 7 samples here, and 3 by 10 because I have 3 samples here. Okay, from my data set, 3 samples have the value no for the feature star. Okay, Now the information gain for the feature star is 1, which is the information gain of the whole data set minus the entropy, the remaining entropy for the feature star. So the information gain when choosing the feature star is 0.01. Now we're going to do the same calculation for the feature gainer. Okay, the feature gainer has 3 values, so it creates to me 3 subsets. So I calculate the entropy in this subset, this one and this one. Then I calculate the remaining entropy, which is the summation of all these entropies, okay, multiplied by the respective values of the probabilities of observing the samples here in the subsets. So 6 by 10, 1 by 10, and 3 by 10, okay? So I have a remaining entropy of 0.8264664, and the information gain for the feature gainer is 1, which is the information gain of the whole data set, minus the information gain of the feature gainer, which is equal to 0.17. So we have the information gain of the 3 features of our data set. So which feature to choose? The feature that maximizes the information gain. So the feature that has the maximum information gain is the feature country, okay? So we are going to choose the feature country to start dividing our data, which means to start constructing our decision tree. Okay. Now we're going to perform the same calculations again, okay, with all the features, and I'm going to simplify here, because if I already chose the feature country to be put in my decision tree, now I have to analyze the other 2 features, gender and star, okay? So I have to choose which features to put here in these subsets, okay? Now this subset is my new entire data set, okay? Now I'll have to calculate the entropy for this data set, okay? Considering it now as an entire data set, and calculate the remaining entropy for choosing feature star to divide this data set, and for choosing feature gainer to divide this data set. Calculate the remaining entropies, and then calculate the information gain for choosing each feature, okay, again. So I'm going to do these calculations for this subset, and this subset I don't have to do anything because it's already pure, okay? So that is why the algorithm is recursive. It calls itself on new and smaller subsets of data. So I'm dividing data recursively. Okay, so because now we know how to perform the calculations, we're not going to perform the calculations all again anymore, okay? What I'm going to do is using the intuition with you. Okay, so if I get this data set here, okay, let's see what features are going to be the best one to divide this data here, okay? If I select feature star to put here, it will generate these 2 subsets. And if I select feature gainer to put here, it will generate these 3 subsets, okay? And one is empty. So which is the best division? Of course, this one, okay? Because choosing this feature to put here, I'm going to construct pure subsets. So the information gain for a feature star is going to be higher than the information gain for a feature gainer, okay, considering this subset. So star is going to be put here, okay? And this is my new data set. This is my new decision tree, sorry. Now I have to do the same calculations with this subset here. So which feature I'm going to choose to put here? Star or gainer? If I choose to divide this data set here using feature star, the resulting subsets are going to be like this. If I choose feature gainer to be put here, okay, the resulting subsets are going to be like this. So which feature is going to give me the higher information gain? This one, gainer, because it produces the more pure subsets, okay? It produces only pure subsets. So this feature is going to be put here. And this is the final decision tree, okay? So with this toy data set, I can show you how to use a decision tree, okay, how to use an algorithm to construct decision trees, okay, to a given prediction target, okay, a given prediction task. So we can extrapolate this for SNPs, okay. So each feature here, country, star, or gender, could be a SNP, okay, with its all different values, okay. But the process would be the same, okay. So suppose I want to construct a decision tree, don't know, to predict the productivity of rice. I want to predict different classes of productivity: high productivity, medium productivity, small productivity. Okay, or I want to predict, for example, the strength of my grain. Okay, very strength, not so strength. Okay, and different targets you can imagine for the rice. Okay, so the calculations are going to be the same. So I think it's easier to show this toy problem, and then you extrapolate to any kind of features and biological features you want. Good. Now, having this decision tree already induced, okay, the final decision tree, we can use it to predict the values for new movies in this case, for new samples of any kind, okay? So, getting, for example, here a new movie, okay? The values of its feature of their features are, for example, for movie 11, country USA, star no, and gender fiction. So what's going to be the class of this movie? Okay, if the country is United States and the star is no, so the movie is not going to make success. It's false. And we are going to perform the same analysis for the other movies, okay? And here, I have a new prediction. Good. Okay. By now, I showed you how to construct a decision tree when my target attributes are categorical. Like I told you, classes of productivity, classes of a movie, okay? But what if the output I want to predict is numerical? So for example, the value of the productivity of the rice, okay? Now the leaf nodes, okay, will contain a mathematical function and not a target and not a class anymore, okay? In the simplest case, okay, the prediction the prediction of the decision tree, okay, can be computed for each leaf node as the average of the values that fall in that leaf node. Okay, so for example, if I want to build a decision tree to predict the productivity of rice, okay, so the prediction for each leaf node, okay, is going to be the average of the production targets of the instances that fell in that leaf node, okay? I'm going to compute this average for all training instances that I used to induce my decision tree, okay? So I'm going to get the average of all these training instances for each node, okay? And these averages are going to be the predictions for the decision tree. Or I can build a linear model, okay? I can fit a linear model in each leaf node. I can fit a linear model using the examples of each leaf node, okay? So this mathematical function is going to predict the value of a target attribute. So for example, here, I have another toy example. So I have, I don't know, it can be here, vehicles, no? Suppose that each row here is a vehicle, and as features we have the potency, the weight of the vehicle, the acceleration, and we want to predict the consumption, okay? So again, each feature here could be a SNP, each row could be a sample of rice, okay? And the target variable could be the production of that sample. So in this case, we fit a regression tree, okay? Where here in each leaf node, okay, instead of calculating the majority class of an instance in each leaf node, we calculate the average of the target attributes of the instances in each leaf node. Okay, the average, or we get the instances that fall in each leaf node and calculate here and fit a linear regression. Okay, so fitting a linear model, for example, we could have in each leaf node a linear model like this one, for example, that predicts the consumption based on this linear model. That's a value multiplied by the potency plus a value minus a value multiplied by the wage plus here a constant. Okay, so this is a linear model. Okay, beta 0 plus beta 1 times a feature plus beta 2 times a feature plus beta n times the n-ism feature. Okay, so we're going to have one of these for each one of our leaf nodes. Okay, now that we know what a decision tree is, okay, we can give the definition of a random forest. So a random forest is a collection of several decision trees. Each decision tree is going to be trained on a subset of instances from the original set, what we call a bootstrap sample. So each decision tree here, okay, is going to have an output, as we saw, because we already saw how to train an individual decision tree. So we know that each decision tree in the forest is going to be its own output. So multiple outputs are going to be used to decide the final prediction for a random forest. Okay, so suppose I have a random forest, I don't know, with 1,000 trees. Okay, and I want to predict the productivity of rice again, if I have a high productivity or a small productivity. Okay, so given a sample of rice, when I give this sample of rice to a random forest, the output is going to be computed based on the outputs of all the 1,000 decision trees. So we can use majority voting. If the majority of the decision trees tells that sample has a high productivity, so the prediction is going to be a high productivity. Okay, and we are going to see how we can use the decision trees to actually select the best features of our data set. So in our case, the best SNPs related to the productivity of rice. Okay. So the idea to build a random forest, okay, is that a large number of uncorrelated trees working as a committee get better results than any single tree. So here, having our original data set, for each decision tree that we are going to induce, we get a bootstrap data set. A bootstrap data set is a data set constructed randomly picking, okay, some samples from the original data set. Okay, and also, okay, these data sets we're going to see, they can be constructed using subsets of the features as well. Okay, so I randomly get some instances and also randomly get some features to construct the bootstrap data set. And then we induce our decision tree. For each decision tree of our forest, we're going to have a bootstrap data set. Okay, and then we induce the decision tree in the bootstrap data set. Okay. So the features and the instances that were not selected to form, okay, not the features, of course, but the instances. The instances that were not selected to form the bootstrap data set are called the out-of-bag data set. So for each decision tree in our random forest, we are going to have a bootstrap data set and an out-of-bag data set. So after training the decision tree in the bootstrap data set, I can evaluate this decision tree in the out-of-bag data set and calculate, for example, the mean square error of this decision tree, the accuracy of this decision tree, okay, depending on my task, if it's classification or regression. Okay, anyway, so as I told you, each tree can be constructed from a random subset of features or attributes here, okay? So the idea is that in a random forest, we have many different trees from each other, and that the combination of these trees make a strong model. And then, for the classification, the final prediction can be obtained using majority voting, as I told you, and for regression, the final prediction can be obtained averaging the individual predictions, okay, averaging the individual predictions of the trees in my random forest. So example here, as an example, I'm getting a new sample, okay, where the features are age, income, sex, and merit, and I want to predict I think I want to predict remember the target attribute, I think it's merit. I want to predict if it's the person is married or not, okay? So, for example, so most of the people, okay, most of the data sets, most of the trees in the forest predicted that the person is not married. So the final prediction is that the person is not married, okay? Okay, good. So remembering the out-of-bag sample that I told you, so we can use its error to select features. So that's a very good characteristic of the random forest. So for each tree, the error of the out-of-bag sample is going to be calculated, okay, error rate for classification, mean squared error for regression anyway, and the same is going to be performed after permuting each feature. And then the difference between the two is going to be calculated and averaged over all trees, okay? So for each tree, we are going to get a feature in the out-of-bag sample, and we are going to change the values of that feature in the out-of-bag sample, okay? So we are going to calculate, for example, the accuracy of the tree for classification problems, the accuracy of the tree in the out-of-bag sample, and then we are going to get a feature. Okay, let's evaluate this tree. Let's evaluate how good is a feature A for this decision tree. So we go there in the out-of-bag sample, and we shuffle all the feature values in the out-of-bag the sample, okay, for the feature A that we're going to evaluate. And then again, we evaluate the tree in that data set. Okay, if the accuracy of the decision tree decreases when I shuffle the data in the out-of-bag sample, that means that that feature was important, because the difference between the accuracy of the tree in the original out-of-bag sample and the accuracy of the tree in the shuffled out-of-bag sample is high. So that feature is important, okay? Because it decreases the accuracy, it decreases the performance of the tree after I shuffled it. So I'm going to do this for all the decision trees that have that feature, and I'm going to average, okay, this difference in accuracy over all features. So this is going to be a measure of the importance of the feature for my data set. And then I can rank all the features based on this measure, okay? And then I can verify what are the most important features in my data set for that given task. For example, the productivity of the rice. Okay, here are some useful links I would like to leave you with. And I'm going to show here to you what I would like to show is how to apply this. Okay. I'm not sure it's, let me increase here. Yes. I hope everybody's seeing. Okay. So here's a SNP data set. Okay. So I'm using R here. Okay. And I just loaded this data set here. Okay. And I'm showing you the SNPs. Okay. The values of the SNPs. And here is the target variable. So in this data set, for example, given here, this is part of a data set, okay? This is a huge data set, but I just extracted a little part of it. So I have 50 SNPs, okay? And I want to predict the productivity of the rice, okay? So as you can see, there are some values missing here. So what I did here is that I've constructed some functions that just replace the missing values, okay? So for example, here, missing values with the most, with the SNP value here, the nucleotide that appear the most in each column, okay? Just to use this data set with machine learning, okay? Okay, now, okay, very good. So I'm showing here just, the mode, okay, the SNPs that appear the most, okay, in each column where I have SNPs missing. Okay, so for example, SNP 5 here, SNP 5, yeah, SNP 5, there's a SNP missing, and the SNP that appears the most in 5 is in the column responding to SNP 5 is T. So I'm going to replace this guy here by T. Okay, just to use in the decision tree. Okay, good. So what I'm doing here, I'm dividing my data set, okay, and training and test data sets. And with this package here, I can construct a decision tree for my data set. So I'm building a formula here. What I'm doing, I'm saying here that I'm going to use all the features to build my decision tree against the target feature, okay? With this comment here, this function, I can construct a decision tree with the training data set. Remember, I divided my data set here into training and test data sets. And here is the resulting decision tree, okay? So it's a decision tree for predicting the production of rice. Okay, so depending on the value of each SNP, okay, I have a productivity being predicted. Okay, so I can consider that for just one decision tree, these are the most important features of those 50 features in my data set. And using this decision tree, I can make predictions using the test data set with this function predict, okay? I don't know if everybody's familiar with the R function, with the R program language here. And what I'm doing here, I'm constructing a table where I am combining the true productive values with the predicted productive values. And as you can see here, I have the predictions, okay, using a very simple decision tree for each sample of my test data set, okay? Okay, and here you can see I just calculated the squared error, okay? The root square error for this data set. Now I'm going to use the other package that's called rpart to construct another decision tree. So the procedure is going to be the same, okay? I'm going to use all targets to construct a decision tree for the target data set, okay? And here, oh, sorry, yeah, the rpart function was called here, and here is my decision tree. So I'm going to plot, okay? I'm just showing the decision tree here, but instead of showing it this way, I'm going to plot the decision tree here with this library here and this function. So this is the decision tree I just constructed with the other package, rpart. So because this is a more sophisticated package, okay, and its hyperparameters are different, I have a bigger decision tree here, okay? So the bigger decision tree, the bigger the decision tree I have, more complex it is more difficult to interpret. So what if I want to decrease this decision tree? So what I can do actually is to verify the errors obtained every time I increase the size of the tree. Okay, so let's get the smallest error here. So for example, here in the level 4, okay, I have an error that is the smallest one among all the errors here. Okay, so what I'm going to do is that I'm going to prune my decision tree based on this error. This error was calculated while inducing my decision tree in the training data set. Okay. So I'm going to actually, yes, and I got here the level 6, okay? But I could have taken the level 5 here. Anyway, what I'm going to do here is that I'm getting here, look, I'm getting the table, okay, in the column CP, see, CP, that's complexity parameter, and I'm getting the complexity parameter in line 6, okay, line 6 is here. So I'm going to prune my decision tree, okay, after this, the split number 6. So applying the pruning here, I have a smaller tree. So compare this tree with this one, okay? And the prediction, okay, the evaluation measure comparing the pruned tree with the original tree are not so different. So now I have a less complex decision tree from where I can get the most important SNPs from my data set, okay, and together with a higher interpretability. Okay, I can convert this to rules more easily. And here I'm just comparing the predictions of the original decision tree with the pruned decision tree, and calculated here the evaluation. See, the pruned decision tree had a smaller error than the original decision tree. Okay, so these are decision trees, but how can we select very good features using random forests? Okay, so again, I'm loading here my data set. Okay, the same data set I used for decision trees. Okay, I'm making a function here. Okay, I'm making a function here again to fill missing values with the SNPs that appear the most in the data set. Okay, nice. So here I have data set with no missing values. Now I'm going to use a library called random forest, okay, and a package here to make some plots. So what I'm going to do, I'm going to perform 100 executions of random forests, okay? So I will have 100 random forests, okay? And I'm going to build a rank for each random forest. For each random forest, I'm going to have a rank with 10 positions. In this rank, I'm going to put the most important features for a random forest, okay? And here I'm building a matrix, okay, that's giving to me the following. For example, see, any row, number of execution. So this is a matrix with 100 rows per 10 columns. So for each execution, okay, so we're going to have 100 random forests. So for each random forest, we are going to have a ranking with 10 most important features. Okay, good. So this is a training loop where what I do is that I execute a random forest. Okay, I separate my training data here in training and testing. And then I execute a random forest, see, with 50 trees, okay, calculating the importance of each feature. And the importance is calculated based on that mean decrease on the mean square error. Again, so I have a tree in my data set. Okay, I calculate the mean square error of this tree in the out-of-bag sample. Okay, and then I shuffle the values for one feature and calculate the mean square error again. If the mean square error increases a lot for the shuffled data set, then that feature, that's an indicative that that feature is important. So I'm going to perform this kind of calculations for all 10 executions or all 100 executions for 100 decision trees. And I'm going to store here, okay, the more important features, the 10 more important features according to this importance calculate that I just explained for each execution. Okay, and at the end, what I have here, see, I'm just showing the head of that data, of that matrix. I just showed you 100 per 10. Okay, so for each execution, for each random forest, what I have is a ranking of the 10 most important features for that data set and for that random forest execution. Okay. And now, what I did here, these are the errors for each of the executions. And what I did now is that I verified all the SNPs that appeared here. Okay, because I have repeated SNPs here, of course. See, for the first execution, SNP 38 was the most important one. For the second execution, SNP 38 was again the most important one, and so on. Okay, so if I get this matrix and use the unique function, I can obtain all the SNPs that are here. So these are the most important SNPs for my data set. Okay, very good. And what I'm doing here is that I'm going to plot a graph, okay, with this ranking. Okay, this plot, okay, what I'm doing here is that I am counting how many times each feature was considered the most important in each ranking. So from 100 execution, SNP 38 was considered the most important, okay, first position in the rank 0, 86 times. SNP 26 was the second most important in the remaining 14 times. The other SNPs did not appear in the first position of the ranking. Okay, and I am calculating this, see, for all the ranks, all the positions of the rank. So here, for example, for the rank 1, for the second position of my ranking, SNP 38 appeared 14 times in the first position. SNP 26 appeared 84 times, okay, in the second position, okay. SNP 38 appeared 14 times in the second position of the ranking. SNP 26 appeared 84 times in the second position of the ranking, and so on. Okay, so I have these calculations from R0 to R9, how many times each instance appeared in that ranking, that position of that ranking. Okay, good. And here I can plot a graph, see, showing the most important features. So for example, SNP 38, as we saw here, okay, it was the most important feature. See, SNP 38 appeared 86 times from my 100 executions of random forests. SNP 38 appeared 86 times as the most important feature. Okay, so in the first position of the ranking, SNP 38 appeared here 84 times. That's why the color blue here, the bar blue, is high. The other 14 times, okay, were occupied by SNP 26. SNP 26, this color here. See? And the same analysis was performed by the other positions of the ranking. So as the positions of the ranking, okay, are becoming, as I get far from the first position of the ranking, more SNPs share that position of the ranking. Okay, so this is a visualization, okay, graph to see what are the most important SNPs for the productivity of rice, okay, using random forests. To validate more statistically my experiment, of course, I have to increase here the number of times, the number of executions. So instead of 100 executions, I would perform 1,000 executions, 10,000 executions. Okay, so then I validate more statistically my experiment. Okay, And having the random forest, of course, I can make predictions for new samples of rice. Okay, so I'm getting here my random forest model, see, and I am doing, I'm getting a random forest. Okay, of course, I made 100 predictions of random forests. Okay, but in order to make a prediction for a new sample, I'm going to execute one random forest again. Okay, because otherwise I would have a committee of random forests, but I want to make the predictions using just one random forest. So I induce a random forest model again using the training data set, and here I am predicting the value of the productivity for that using that model, okay, and using the test data set. And what I'm doing here is constructing a table comparing the predictions and the true values, okay, here. The true values of the production and the predictions for the productivity of the rice. And if I compare here the error of the random forest compared with the error of the decision tree, see, the error of the random forest is smaller, okay? And what I can do, of course, is that I can save, okay, all this information and then use this model then again for here for making predictions. Okay, yeah, that's it. I think it's more or less what I wanted to show you. So now I hope you understood how you can build a decision tree. Okay, and I hope you know the mathematical foundation behind building a decision tree. Okay, that can be used to predict targets for any kind of biological data and can be used for the rice, which was our case here. Knowing how to build a decision tree, you now know how to build a random forest, okay? That's just building hundreds of decision trees using out-of-batch samples. And now, use for each decision tree of the forest, you can compute its error based on the out-of-batch sample, okay? And then you do this for all the features in the decision tree, and you average, okay, this out-of-batch error, the difference between the out-of-batch error and the out-of-batch error when you shuffle the feature, you average these differences over all the decision trees in the forest. And then you rank the features based on this calculation of the importance of each feature. And having this ranking, okay, you can indicate the most important SNPs, for example, for, in our case here, the productivity of the rice, okay? This is just to finalize, this is a project, okay, that we are doing together with Embrapa, Arroz e Feijão. They are providing us the samples of rice, the target values they want us to predict, and then we provide them with the most important features we find, okay? And then they have to validate this in lab, okay? I think that's it from my side. If we have questions,